Hey everyone, back to a new awesome video, and today we're gonna continue with our series about classical mechanics. Today we will finally start combining rotational and translational motion. In the next three videos we will explore the problem of a rotating ball. Today we will set up our system, then we will introduce the three types of rotation, and then we will start exploring the non-slipping case. So let's start. Great, let's start analyzing our system. Here we have our ball, even though it looks a bit wobbly, but we'll assume its radius is constant and it's equal to r. Then we have our center of mass, the origin with reference frame A, and we'll call this it's the ground frame basically, and we're also going to consider the center of mass frame, which will be really useful when analyzing this situation. Moreover, we have a point P on the circumference of our ball that we're going to use to analyze the situation. We assume that this ball is moving forward with a velocity v. Then we're also going to have three very important vectors. First of all, we'll have the vector connecting to the center of mass. We'll call it capital R. Then we're going to have the vector connecting from the origin to our point P. And then we're going to have the vector connecting from our center of mass to our vector P that we'll call RCMP. Now, we observe that we have this vector triangle that allows us to relate these different variables. Specifically, we find that RP equals capital R plus RCMP. And if we differentiate all of these quantities, we'll find that this v of the point P is equal to the velocity of the ball, this v, which is really the velocity of the center of mass, what we're considering here, plus the velocity in the center of mass frame of P, this change. As this ball is going to be rotating with a constant angular velocity, W, we conclude that this value is going to be constant all over the rotation. So again, in the center of mass frame, the velocity of the points in the circumference of the ball are going to be constant. It's not going to change through time. Right? Now, let's analyze this situation in the center of mass frame. We observe that we can express RCMP as a function of this angle theta that is also related to our angular velocity. So we find that this value, RCMP, is going to be equal to cos theta j hat plus sine theta I hat RCMP, being this the magnitude of the vector, which this is no other thing than the radius of our ball. And of course, we are using our usual vectors that we should denote also in our system over here. Now, if we differentiate this quantity to find this velocity, what we're going to find is that v find that this velocity is equal to Rw cos theta I hat minus sine theta j. If you hadn't recognized it already, this expression is no other thing than our R vector, which points in this direction. And this other expression is our theta hat vector. that points in this direction. We observe that due to the way that we have defined our unit vectors, I hat and j hat, this angular velocity is going to be negative as it's pointing towards the inside. It's rotating this way and therefore it's pointing towards the inside. And our k hat vector is pointing towards the outside. So these directionals of our theta, it's negative, gives negative values of theta. And this w, it's also negative, as we said. So the velocity is going to be pointing in this direction. And as we said, it's going to be constant all throughout the path. It's going to be always equal to rw theta. Now, let's analyze the situation in the ground frame. Let us analyze the total velocity of our point P at 4 different points. The top, both sides, and the bottom. At every point, we're gonna have a constant velocity of b, c, and p, which is gonna be equal to rw in magnitude, and it's always gonna point tangent to our sphere. So we'll have this velocity, this velocity, this velocity, and this velocity. Moreover, at every point, we're also going to have this constant velocity that is going to be added. So we would have, it's noted in red, this velocity, this velocity, this velocity, and this velocity. The magnitudes, the relative magnitudes of these two vectors, we don't know them yet and will depend on our specific case that we are studying, as we'll see later on. And the total velocity, this Vp, is going to be equal to these vectors in general, with the exception of this bottom one, which will be the way in which we differentiate between the different types of translation and rotations, motions that we have. All right, let's state the different cases that we have. Imagine that we have on our plane two different instantaneous positions of the ball. Here we have our ball at time 0, in which our point P is vertically right above our center of mass, and then we have our position at time delta t. Note that even though the drawing is not correctly portrayed, the point of contact of the ball with the ground should be right below the center of mass in every case. Same here. Therefore, we also need to indicate here the amount of displacement that the ball has gone, delta xcm, which is no other thing than the velocity of the ball, b, or bcm, if we want to specify, times the time interval that happened. Moreover, we would also like to see how much has the ball rolled, which is this circumference path. And we know that if this angle is delta theta, this path length is going to be r delta theta. And is the relationship between these two quantities the one that is going to determine whether the ball is skidding, slipping, or rolling without slipping? Therefore, first case. First case is rolling without slipping. This is the simplest case in which the ball moves and doesn't slip from the ground. There's always friction, and the point of contact only touches the ground at one specific point. Therefore, in this case, delta x, center of mass, the movement that this has gone through, is equal to delta s, this path length, or in other words, the BCM times delta t equals to r delta theta. Moreover, in this case, if we take the infinitesimal limit and we divide by delta t, and we let the delta t go to 0, basically to dt, we get that BCM equals RW. And if we remember our previous diagram, that would be equivalent to two vectors that were pointing in opposite directions totally canceling. Therefore, in this case, the point of contact is instantaneously at rest once it touches the ground. Then let's consider the other two options. In this case, delta S is bigger than the delta XCM. This corresponds to the ball slipping as if it was in a slippery surface, and therefore when you try to rotate it, the ball doesn't move. It just rotates in place and moves a tiny bit. This is also equivalent to the BCM, velocity in the center of mass, being less than RW. And lastly, we have our third case, which is skidding, that corresponds to when you launch the ball, for example, on ice, and it's rotating a little bit, but mainly the motion is moving forward. In this case, delta XCM is bigger than delta S, and BCM, the velocity of the center of mass, is bigger than RW, the instantaneous velocity at those points. From now onwards, we will solely analyze the case of rolling without sleeping, as it's the simplest one and it's the one that allows us to get really deep onto the different variables and different magnitudes that appear on this problem. Now, let us analyze more carefully what happens in the case of rolling without sleeping. Imagine that we have our ball again in the ground frame, and we're specifically interested on the contact point, which appears to be below the ground. Just imagine that the ball is a little bit more up and it actually works. Then, as we analyzed previously, we're going to have two vectors opposing each other. First of all, we're going to have the vector that corresponds to the rotation of this ball around the center of mass, how it revolves around it. But then we also know that the center of mass is moving with a velocity of b. Therefore, it's going to be pointing over here, the BCM. Earlier, we didn't know the magnitude of this vector sum because these two vectors might cancel each other, might point over there, might point over here, which is basically the three cases that we explored earlier. In this specific case, rolling without sleeping, we do know the magnitude of these two vectors. We first calculated BCMP previously on our first analysis, which gives us that this is equal to RW theta hat. And we also calculated BCM previously on this specific case, which gave us that the magnitude of this vector must be equal to RW. Then, from our analysis, we know that these two vectors are opposing each other for sure. Therefore, what this means is that the B of P, BP equals RW theta hat minus RW theta hat, and therefore it's equal to 0. At this specific point, this makes us conclude that the point of contact with the ground is instantaneously at rest when we are rolling without sleeping. And this will be a very important fact that will allow us to analyze this problem properly. Great, that's all for today. I hope that you understood everything and you are starting to get a sense of how we can combine these rotational and translational movements together. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!